The nature of dark matter, the invisible substance that accounts for the majority of the universe's mass, is one of the greatest scientific puzzles today. For many years, scientists have been looking for hints about what dark matter is and how it functions, but they have not yet discovered any concrete proof of its existence. Its gravitational effects on ordinary matter, like stars and galaxies, have instead led them to conclude that it is present. Dark matter, however, is not universally accepted as a fact. Alternative theories contend that the observed phenomena can be explained without the use of dark matter by altering the principles of physics or gravity. These theories contend that dark matter is a myth and that our current knowledge of the universe needs to be revised. But how can we definitively resolve this argument? Is it possible to determine whether dark matter exists or not? A new space telescope may be able to accomplish that, though. Its name is Euclid, and it has just begun to open its eyes. By charting the distribution and evolution of dark matter and dark energy across cosmic history, Euclid is intended to explore the dark cosmos with unprecedented precision and detail. By doing this, Euclid will assist us in determining whether or not we should update our current ideas of physics and gravity. In this video, we'll examine Euclid's operation, what it has observed thus far, and what it anticipates learning in the future. You can watch our prior episode to learn more about Euclid and how it will work with the James Webb Space Telescope. Let's explore the universe's shadow side with Euclid for the time being, though. Launched on July 1, 2023, the European Space Agency mission Euclid is intended to research the dark universe, which is made up of dark matter and dark energy. We don't know what these mysterious substances are or how they function, but they account for nearly 95% of the universe's total mass and energy. Galaxies and clusters are held together by dark matter, an invisible kind of stuff, which also acts as gravity. On the other hand, an unknown component known as dark energy accelerates the universe's expansion over time. Euclid intends to investigate these events in order to give insight on some of the most important cosmological issues, including the universe's creation, progress, and end. Euclid has two potent cameras on board, a visible imager called ZSS, and a near-infrared spectrometer and photometer called NISP. To accomplish this, with a 10 billion light-year field of view, these cameras are capable of capturing photos of billions of galaxies. They can thus observe what the universe looked like a few billion years ago. Euclid can map the distribution and evolution of dark matter and dark energy over the course of cosmic history by measuring the sizes, shapes, locations, hues, and distances of these galaxies. How do these cameras operate, though? To catch different light wavelengths, they use various sorts of detectors. The VS camera records visible light using CCDs, charge-coupled devices, the same kind of technology used in digital cameras and smartphones. The NISP camera records near-infrared light, which is a form of light that is undetectable to our eyes but can pierce space dust and gas, using Hawaii 2 RGs or H2 RGs. A unique function is also present in the NISP camera. A grism, which combines a prism and a grating, can divide the light into its spectrum. This enables it to calculate the redshift of galaxies, which is a measurement of how much the universe's expansion has distorted their light. Knowing a galaxy's redshift allows us to calculate its distance from us and rate of expansion. Compared to other space telescopes, these cameras have several advantages. For instance, they have a very wide field of view, allowing them to quickly cover a larger portion of the sky. They can see more details and dimmer objects thanks to their extremely high resolution. Additionally, because of their extremely broad wavelength range, they can observe more varieties of galaxies and stars. These cameras do, however, encounter significant difficulties. For instance, the extremely high radiation levels in space can harm its electronics and sensor. Additionally, they must endure extremely cold temperatures, which may impair their functionality and stability. Additionally, they must properly calibrate their images in order to correct for any distortions or inaccuracies brought on by their optics or environment. Euclid's cameras were examined and calibrated both before and after launch, utilizing a variety of techniques and tools to address these issues. To confirm their accuracy and quality before launch, they were put through rigorous simulations and trials on Earth. They were put in vacuum chambers, for instance, to simulate spaceflight. Additionally, they were exposed to various light sources that replicated the stars and galaxies they would see. Additionally, they underwent calibration using specialized equipment that assessed many aspects like their sensitivity, alignment, focus, distortion, and noise. They were additionally examined and calibrated using actual space observations after launch. They captured photos of well-known stars and galaxies, for instance, which they use as a baseline for their observations. Additionally, they photographed empty areas of the sky to use as backgrounds for their subtraction. Additionally, they captured photos using various filters and exposure periods that served as inputs for their study. Some of the challenges they ran into during these testing and calibrations had to do with how complicated and variable their devices were. For instance, they had to consider how temperature variations might affect their detectors and optics. Additionally, they had to make adjustments for any pointing or focus drifts or shifts brought on by vibrations or thermal expansion. Furthermore, they needed to eliminate any stray light or cosmic rays that would taint their photographs. Some of the accomplishments they made during these calibrations and testing had to do with the efficiency and dependability of their instruments. For instance, they verified that their detectors and optics were performing according to plan and within the parameters they had specified. Additionally, they checked to see if their photographs were clear and sharp and agreed with their models and forecasts. Additionally, they showed that their cameras could achieve their scientific objectives and were prepared to do so. Following these trials and adjustments, Euclid's cameras were able to capture their first test images from orbit. On July 28, 2023, these images, which provided some incredible vistas of the universe's stars and galaxies, were made public. Let's examine a few of them to see what they show. The first image we view was captured by the VIS camera and depicts a region of the sky with around 100,000 stars and galaxies. With blue being the brightest and red being the palest, the colors in this image stand for various brightness levels. With a resolution of around 0.1 arcseconds, or 500 meters at a distance of 10 billion light-years, this image can distinguish between objects that are as close as 0.1 seconds of arc. This image is noteworthy because it demonstrates the capability and accuracy of the VIS camera. Compared to earlier or contemporary space telescopes like Hubble or James Webb, it can take far sharper and deeper photos. In contrast, Hubble has a field of vision of just 0.01 square degrees and a resolution of around 0.05 arcseconds. James Webb has a field of view of only 0.002 square degrees, but a resolution of roughly 0.1 arcseconds. Euclid is the best tool for mapping the large-scale structure of the universe since it can combine high resolution with a wide field of view. In the second image, which was captured by the NISP camera, we can see a region of the sky that is home to roughly 200,000 stars and galaxies. With blue having the shortest wavelength and red having the longest, the hues in this image indicate various near-infrared light wavelengths. This image's resolution is approximately 0.3 arcseconds, which is a little less than the VIS image. This image is noteworthy because it demonstrates the sensitivity and adaptability of the NISP camera. It is capable of taking pictures that are significantly wider and redder than those produced by Hubble or James Webb, two past or current space telescopes. In contrast, Hubble can only detect near-infrared light with a wavelength of up to 1.6 micrometers. James Webb can detect near-infrared light with a wavelength up to 5 micrometers, but not below that. A vast variety of galaxies and stars are visible to Euclid in the near-infrared range, which ranges in wavelength from 0.9 to 2 micrometers. These sample images taken by Euclid's cameras are only a small taste of what this incredible space telescope is capable of. In the next years, Euclid will continue to capture images similar to these, which will be used to explore the dark cosmos in unparalleled detail and precision. Euclid will do this by explaining some of the most fundamental cosmological mysteries, such as the origin, evolution, and final destiny of the cosmos. Thank you for watching, and if you liked it, please subscribe to our channel to see more content just like it. Keep exploring and being curious until next time.